Hello, we are going to solve this sprinkler problem where we have an oscillating sprinkler going between 45 and 135 degrees, and it's watering a lawn. They give us this nice diagram here. So we see that the lawn is getting watered between these two X positions from here to here. And just to get an understanding of how these sprinklers work, let's look at this video I found on Facebook where someone is very happy with their sprinkler and posted a video of it. So you see it's adjusting its angle, water's coming out of it. So it's watering the lawn from looks like about here to here. And that's the basic idea. This one looks like it doesn't go quite to 135 degrees, but that's how it works. And the first thing they ask us to do in this problem is to find the dx/dt. Um, so before we even do that, let's just look at what x is and look at the variables that they're using here. They're saying that v is the speed of the water, and the speed of the water is not going to change um, over time. It's a constant speed. It's coming out of the hose, um, and it's not going to change. So it's just going to be a constant when we take the derivative. Now, theta is also theta is actually changing because at one time we're at 45 degrees and at another time we're at 90 degrees and the sprinkler is actually oscillating. So theta is changing over time, which means when we take this derivative, we do have to use the chain rule for theta, but not for v. Um, okay, so dx dt is going to be equal to, I'm just going to take out our constants. So these are the constants. And then the derivative of sine of 2 theta is just cosine of 2 theta. And then we use the chain rule to get a 2. And then use the chain rule. Um, we have d theta dt because theta is a function of t. And this can be simplified. I know I'm kind of running out of space here, but I'm going to put my constants in the front. So we have this, and they're asking us to explain why the lawn sprinkler does not water evenly. And let me just check, because I saw this earlier. Check that I have this right so far. Yeah, that looks good. All right. So why is it not getting watered evenly? Well, this is the rate of change that we're moving along X. So if this rate were a constant with time, then we would know that the lawn is getting watered at a constant rate. But this is not a constant. Here is a constant. This is a constant. But this here actually changes with time because theta changes with time. So that's our answer. dx dt tells us that the distance, the position that we're at, our horizontal position changes with theta, and theta changes with time. So we're not watering evenly. Now it says what part of the lawn receives the most water. Okay, well, to see where we're receiving the most water, we need to find where dx dt is a minimum. Because if we are traveling slower over this horizontal distance, let's say we're going really, really quickly here, and then we're moving really slowly here, and then we're moving really quickly again, which is actually what happened. So it kind of gave away the answer. But wherever we're moving slower is where we're watering more of the lawn. So we need to find where we're moving the slowest. So to do that, to find the minimum of dx dt, we find the second derivative, dx squared d squared x dt squared. Yeah. So the second derivative uh, would just be gonna keep our constant term in front here. And now the derivative of cosine 2 theta, it's negative sine of 2 theta using the chain rule. We get this, and we're just going to simplify. Um, all right, let me double check with what I got earlier. Yeah, that looks right. So we have our second derivative. To find the minimum of the first derivative, we set the second derivative equal to 0, and I'm just going to erase the work for the first derivative now. No, it's a little cramped here. So 0 is equal to this, but this whole part in front is just a constant. So I'm going to divide by that, and we're just left with sine of 2 theta equals 0. So 2 theta is equal to 0 degrees, 180 degrees, 360 degrees, and then theta would be equal to 0 degrees, 90 degrees, and 180 degrees. But two of those angles are not in our domain. Um, so we're left with theta is equal to 90 degrees, right? But this is just where the second derivative is equal to 0, not necessarily our minimum. So let's actually see how the second derivative changes around this point. So before 90 degrees, our second derivative would be, let's say, at 45 degrees, um, somewhere in between 45 and 90 degrees. So like 75 degrees, we would have sine of 2 times 75 should be sine of 150. That'll be positive, right? So this whole term is going to be negative, and then it'll become positive after 90 degrees. So we see we're decreasing speed up to 90 degrees, and then after 90 degrees, we're increasing speed, which means that we are slowing down. We're moving really quickly as we're getting closer to 90 degrees, but then we're slowing down. So as we slow down, we're watering more because we're spending more time on that section of the lawn, and then we're speeding up again as we go to 135 degrees. So what area of the lawn is receiving the most water? The section of the lawn around 90 degrees would be our answer. And let me turn this off now.